It is widely assumed that Einstein's general theory of relativity cannot be combined with quantum theory. At least, so far, nobody has found a truly conclusive way. In this presentation, it will be shown that the job was in principle already done by no other than the German mathematician David Hilbert, and there is no need to combine quantum theory and general theory of relativity because the latter already contains the first. A theory of everything, for which we are aiming here, should not only contain Einstein's general theory of relativity, but also all major quantum equations, and it should also explain the appearance of what we describe as matter. In previous presentations in this series, we have already shown how we can extract the Klein-Gordon equation from the Einstein theory of relativity, this was in part 2 of our videos, and that matter does not need to be postulated, this is in part 1. In this presentation here, we will concentrate on the metric derivation of the Dirac equation as one of the most important relativistic quantum equations. The Dirac equation is a matrix equation which contains the Dirac gamma matrices and the beta matrix. Even though on this slide we only give those matrices for the case of four-dimensional spacetimes, in the presentation we will derive general metric Dirac equations for n dimensions. Our starting point is the so-called Einstein-Hilbert action, a variational integral based on a Hamilton extremal principle. Already in 1915, it was the great German mathematician David Hilbert who derived Einstein's field equations from such a fundamental minimum principle. What Hilbert apparently did not see was that his formula in fact contained much more than just the Einstein field equations, but that he had also found the fundament for quantum theory. In this presentation, we will now show what Hilbert had missed, or, taking Hilbert's genius, simply not considered important enough to be mentioned at all. It should also be mentioned that the Dirac equation was not postulated before 1982, and so Hilbert, who had published his word formula 13 years earlier, had no chance in seeing the need to extract something as weird as Dirac's matrix equation with its even weirder spinor solutions. As we have already shown in part 1 of this series that we do not need the matter term Lm nor a cosmological constant to obtain matter, we set both lambda and Lm equal to 0 and just proceed with the curvature of spacetime known as the Ricci scalar as the kernel within our variation. Now, by following Hilbert's classical derivation, we obtain the so-called vacuum Einstein field equations. Things change, however, in a rather interesting manner when introducing a slightly adaptive metric tensor with a scaling factor as shown here. Hilbert's variation then yields a much more complex kernel. Please note that this kernel can directly be simplified by demanding the scaling function to fulfill a special condition. We treated this path in our second part of this series, where we derived the metric, which is to say generally quantum relativistic Klein-Gordon equation. From here now, we could simply repeat our evaluation with respect to the Klein-Gordon equation, see therefore our corresponding previous presentation on this matter in part 2, and then apply Dirac's strategy to factorize the Klein-Gordon equation. This, however, will only lead us to the classical Dirac form and not a metric generalized one. Thus, we will avoid the condition for f and proceed as follows. At first, we split up the variated contravariant metric tensor into its scaling and its tensor part as shown here, and result in two equations, a scalar and a tensor one. In this presentation, we ignore the tensor equation, for example by simply assuming that the variation of the metric tensor gives 0. Then we intend to fulfill the scalar, which is to say the first equation, by demanding the kernel of the integral to be equal to 0. This gives us the following partial differential equation, and by inserting the simplest possible setting for the scaling function f, we get things to clear up a little bit. In the next step, we add in the Dirac starting point, where he assumed that A, the spacetime can be assumed Ricci flat, and thus r equals 0, and B, the Laplace operator has an eigenvalue m squared. Now, by using the connection between the Dirac gamma matrices and the metric tensor, we can directly derive the metric generalized Dirac equation as shown here. As one of the factors in the last line suffices to fulfill the whole equation, we easily recognize the Dirac equation in its classical form. We realize that, in our metric generally relativistic theory, the metric scaling function, which is nothing else but a volume factor, is just equivalent to the quantum theoretical wave function. Just as with the classical Dirac theory, however, the functions Fe have to be Laplace functions. It should be pointed out that, apart from the r equals 0 condition and the Laplace eigenvalue condition used here in order to follow the original Dirac approach, there are also other options to metrically derive masses and potentials via additional dimensions. This will give generalized Dirac equations for curved spacetimes in arbitrary dimensional spacetimes. The interested reader may find more information in the books shown here or other publications of this author. We explicitly want to point out, however, that we do not consider us the first to have found the connection. In principle, namely, it all was already inside Hilbert's ingenious approach, and he only could not see it because, at the time he wrote down his equation, the fundamental equations of quantum theory were not yet discovered, and his main goal was the derivation of the Einstein field equations, and thus, as Einstein had not bothered about also finding quantum equations inside his general theory of relativity, Hilbert, as a mathematician, obviously saw no need to consider the broader spectrum residing in his approach. These new insights open up a variety of possibilities for the most astounding developments, be it inexhaustible sources of energy, future weaponry, metric artificial intelligence, quantum gravity computing, or completely new, and what is much more important, truly unbiased and most holistic modeling tools for almost all sorts of problems. And how could such developments be realized? Well, the optimum is the global approach aiming for the quantum gravity computer and naturalized AI, which is a Manhattan-sized project. How this disrupts everything and makes the owner the global monopoly to just everything can be extracted from the material presented in this talk. The next smaller step is just the naturalized AI, which still is a small Manhattan project. This too already reaches very far and propels the owner into a global monopolistic and long-time leading position unless somebody achieves a takeover via a working quantum gravity computer tech. Everything else are service projects.